All right, so let's talk briefly about the graphs on this lab, and then we'll move on to where we're going next. Notice from the background information of the lab, we're using this relationship, that the wave speed for any wave equals the, what's lambda? Wavelength times the frequency. That's true of any wave. In this example, we are talking about a sound wave, and so we can find the speed of sound if we know something about wavelengths and frequencies. So I told you you're going to do two graphs. One graph is just going to be the traditional, what you expect, the dependent variable versus the independent variable. In which case, what's the independent variable? What did you manipulate? Frequency, right? In other words, you grab a different tuning fork each time, and one of the properties of the tuning fork is how fast the little tines move back and forth. And it's dependent on the tuning fork's what? Length. Right? How long the tines are. The longer the tines, the more moment of inertia, and so the longer it takes for it to complete one cycle, which decreases the frequency. So you picked different tuning forks, which mean you had different frequencies. And then you measured what? The wavelength. The wavelength. And the way you did that is you set up a wave in a column of air that looks like this. The bottom of the column of air was the water, and so it was closed. So that made it become a node. And when you got the right length of column of air for that frequency, it set up a what? A standing wave, which is what we call resonance. We caused it to resonate. That's what made it get really loud. Because at the top of the air column was then what? Yeah. An antinode, right? There's constant constructive interference happening at the top of that column, which caused it to be really loud. Now, that standing wave then I could extend up here, and I'd have another node up there, right? So what is this height compared to a wavelength of that wave? Think about what you did in lab. What length is this compared to a wavelength? How? Double? No, a fraction of it. A fourth. I was right. It's a fraction of it. How did you know that that was a fourth? Because when you got that column of air, what did you do with it? Multiply by 4 to get the wavelength. Hopefully. Okay. Now, if what you got really was the very first antinode, then you multiply it by 4 to get the wavelength. Now, some of you were just talking about this with the group back there. Some of you inadvertently didn't get the very first antinode, and so you ended up getting a wavelength that was half of what it should have been. If you get your data points and you start seeing what looks like two sets of groups, come talk to me. We might be able to easily fix that by just adjusting for what happened. Okay? Now, so this is the way we got the wavelength. So we could do wavelength on the y-axis and frequency on the x-axis. And as a matter of fact, you will do that. That will be one of your graphs. What shape do you expect to get? What?
Hyperbola?
Hyperbola. Why?
I just wrote it down. Because they're inverse.
Because they're inverse, right? As frequency gets larger, wavelength must be getting smaller, and vice versa. And so I'll get a hyperbola. Actually, that shouldn't intersect. Right? It should be hyperbolic. So when you get ready to do your best fit curve, it's going to be what type of curve fit? Maybe a power.
Power squared.
And the power is going to be
2, 3, 4, 5, 6.
1 over x is x to the
Negative 1.
negative 1, yeah.
Oh, we just came from that one.
Yeah.
We're about to, I want you to know that one in a row. This scheduling department totally screwed that.
Yeah, that's what we're going to blame it on. All right, so
I blame them for not getting it.
don't worry, I won't tell me, at least not yet. All right, now, so it's a negative 1 power. So one of your curves is going to be a power fit, and it's going to be, because it's going to be hyperbolic. And we expect the exponent to be negative 1-ish. Okay? Now, the other thing I say, though, is I want a prettier graph. I want a linear fit graph. So tell me, what are you going to graph in order to get a linear fit? 1 over the wavelength, right? Because if I take one of these and divide both sides by, for example, 1 over wavelength equals frequency. Or I could do the opposite, right? I could do 1 over frequency equals wavelength. Same thing. In this case, I would put frequency on the y-axis and 1 over... Actually, no, I'm sorry. Let's do it this way. Let's do it the other way. It'll be cleaner, and you'll see why in a second. So do wavelength equals speed times 1 over frequency, so that on the y-axis is wavelength, and on the x-axis is 1 divided by frequency. Now, what are the units for wavelength? Who?
Hertz.
Yeah, thank you. Meters.
What?
Wavelength is the length of the wave, so it's in meters. What are the units for 1 over frequency? 1 over hertz. What's 1 over hertz? What is hertz?
It's the air velocity. Because it's 1 over frequency.
Well, all right, look up here. Hertz is cycles per second, right? That's 1 over seconds, or seconds to the negative 1 power. Top right. So, if I do 1 over hertz, that's 1 over seconds, which is seconds. So the units on this axis are seconds. Sorry, the wrong answers were too loud for the right answer here.
Wait, who's that second?
So what's this going to be about? It's going to be what shape? Linear. And the slope is going to be right? Because this is y equals mx. So the slope is the speed of sound. And it's in what units? Rise over run, meters over second. Okay?
Wait, why do two different graphs?
Because one is just the traditional independent on the x-axis, dependent on the y-axis, and the other is we want to graph something that's going to give us a linear fit. And that's going to give us two different curve fits. Here's what you're going to do with those. You're going to look at the r squared values. And the one that has the highest r squared, which is what we call the correlation value, or regression value, the one that has the higher correlation, that's the one you're going to use as your observed speed of sound. So for example, I might get something over here where this gives me the speed of sound is 290, and it had an r squared value of 0.84. And on this guy, the slope might be 310, and it had an r squared value of 0.87. Which speed of sound am I going to use? 310, right? Because the r squared value for that graph was higher. So graph both of them, give me both graphs, but when it comes time to do the error analysis, to calculate percent error, only do the one with the higher r squared value. Unless you want to do both, you can, but that's not necessary. Okay? Questions? Okay. So that's your graph, your graphs for the lab. Now, let's move back and pick up where we left off with waves. Before the break, we were talking about waves, and what did we discuss? Give me as much pertinent information about waves as you can remember off the top of your head. Okay, good. Two types of waves, longitudinal waves and transverse waves. The difference being, good, the direction the medium moves relative to the wave itself. Where it's parallel on, yeah, those are the parts of the wave. Yeah, if a longitudinal wave, the wave moves parallel to the media, and in a transverse wave, they move perfectly. Now,
Wait, are we all going to be on like a different test from the last test?
yeah, we're building on that, and so you're still going to need to know this information. Now, what can waves do?
Anything they want.
Okay, they move,
The propagation of crazy things.
usually through the medium. Let's talk about media for a second. The type of wave we've dealt with so far is mostly sound, and it's what type of wave?
Longitudinal.
Longitudinal or compressional. And the media that the sound waves are using right now is air. Can it use other media? Water, solids, right? Put that down on the desk. Okay. So sound can move through any number of media, and it's always compressional. Now, does it require a medium? Sound.
Yes.
Yes. And remember we talked about that's one of the Star Wars things, right? If there's an explosion out of space, you're not going to hear it. There's no sound, there's no matter to carry the sound waves. As opposed to,
So what happens to that energy?
it has to be released all in the form of heat and light.
So the explosion would be a lot hotter in space than it would be on Earth.
It would be hotter. I don't know when you say a lot. I don't know what percentage, but yes, it would have to be larger. Now,
What is sun so hot?
does it matter?
The valid question.
It's okay. It's why we get more electromagnetic energy from the sun than we would if we also heard its reaction to this process.
Wait, does the sun make sound?
If there were a media, yeah. If you were inside the sun, then I suppose you would hear it. If you were inside the sun.
What noise do you suppose it would make?
A
logical assumption.
Sound like a thermonuclear weapon going off.
Go like that for a while.
That's exactly what it sounds like. Hey, as opposed to light waves, which do not require medium, and we're going to develop the concept of light waves a lot, not only the end of this year in electricity and magnetism, but those of you going next year will get even more into it. But for now, all you need to know is that a light wave is, whereas in a sound wave, it's the moving of the matter, right, the molecules closer together and farther apart. In light wave, it's a changing electric field that's causing a changing magnetic field. So you don't have to have any matter. It's just two changing fields interacting with each other. And so that's how it travels without a medium. Again, we'll get into more details as time goes on with the lecture. Now, but the bottom line being light, or what type of waves? Transverse. Right? All electromagnetic radiation is transverse waves. Now, what else do waves do?
Reflect.
Okay, they reflect. And so we've talked about reflection. Reflection is that's a really bad C.
Wait, do like symphony places, like orchestra places, do they absorb waves or reflect them?
They usually absorb.
So
Well, actually, I'm sorry, back up. In like a performance hall, they're going to reflect it, but they're going to direct how the reflection takes place. In a recording studio, it absorbs so that you don't have the reflection.
what are those like things like the like pyramid things in the top of the ceiling? Like what do those do?
Like in a performance
Yeah.
center, it's directing the reflections so that it doesn't have, a flat surface will have a different interference pattern down the bottom, which we'll kind of get into. Whereas curving that surface or angling that surface causes the reflections to then not interfere with each other, so you don't have as much of that translating going. So reflection that we already discussed, and by the way, again, you don't have to know the particulars of why, but a hard reflection involves a phase shift, whereas a soft reflection doesn't.
Oh, we don't need to know.
That you don't need to know this year, but again, planning seeds for next year. But reflection then is the bouncing off of a barrier of a wave. Now, one of the most common examples of that is, what am I holding?
Hammer.
Hammer. How do you know?
It looks like a kid.
It looks like a hammer. How does it look like a hammer?
Because the light is so reflecting off of it, so
Because it's good. Light waves are reflecting off of this hammer and then bouncing to your eye. Which, when it hits the photoreceptors, like the rods and cones in your eye, just like in the sound, in the cochlea, different sound waves, different frequencies of sound waves stimulate different nerve impulses to your brain. Same thing with your eye. Different amounts and frequencies of light set off different photoreceptors in your eye, causing you to send different electrical impulses to your brain, where your brain then makes sense of it. And so the light entering your eye came from where?
Sun.
Okay? The sun and or these light bulbs. That light from that light source hit the hammer and then reflected off the hammer and hit you in the eye. And your eye made sense of it and said, hey, that's a hammer. So that, if I do this, you can't see it. I mean, I even can, but if we didn't have the sunlight from outside or that lamp over, would you be able to see the hammer? No. No, because the hammer itself is not giving off light itself. Right? It's not providing a light source, and so you're not going to see it if there's no other light reflecting off of it.
How come you can see stuff that's black then?
Ah, good question. First of all, you're not really seeing, first of all, nothing's really completely black. Except for what we call a black body. Right? It's a hypothetical thing that absorbs all of the energy incident on it and only radiates off perfect radiation. Right? But if something were perfectly black, you would see it in the sense of
Everything around it.
exactly. It's contrast. You see the light around it, but you don't see any light coming from there, and so your brain says, hey, there's a hole that's a black object. Yeah. Okay? Now, back to the question, by the way. All right, now, so when I see an object, I'm seeing the light reflected off the object, unless, it's producing light itself. Okay? So most things I'm seeing just light reflected off them.